Thanks for the introduction, Kevin. Thanks for all the great souls who chose to attend this talk on Friday afternoon and not flying out early or not being able to catch an early flight as well. um, so this is a joint work that I did at University of Wisconsin with Yinqian Zhang from Ohio State, Ristenpart, who is now at Cornell Tech, and Michael Swift at Wisconsin. Infrastructure as a service public clouds like Amazon EC2 provide an interface to the customer to launch and terminate virtual machine instances on hosts that are provisioned by the cloud provider. All these providers practice multi-tenancy, where two or more customers share the same host to run their VMs, which is also increases resource utilization for the cloud provider and drives down the service cost for everyone. But multi-tenancy, along with openness of these public clouds, also gives rise to an important security issue of cross-VM attacks, as a potentially malicious user could place the VM or collocate his VM with any other VM on this public cloud. In this work, we do an extensive study on these three major public clouds, which includes Google Compute Engine, Amazon EC2, and Microsoft Azure, and show that attackers can actually cleverly use this cloud interface and launch VMs of their own and collocate with one of a set of target VMs at a really, really high probability, and can do some cases really at a really low cost, as low as 14 cents. In the cloud software infrastructure, there are two important pieces that are supposed to provide security against these collocation attacks. One is the placement policy, which is generally unknown to the cloud user, which schedules VMs on hosts of the public cloud data center. Hence, this controls collocation between multi-tenant VMs. The second piece of software is the hypervisor that is responsible to provide isolation between multi-tenant VMs in a single host. We all know that there are a ton of works that have looked at exploiting this lack of performance isolation at the hypervisor, including the one which was presented earlier. But in this talk, we're going to focus on looking at the placement policy, and if an attacker can actually use or game this placement policy to achieve higher chance of collocation. As some of you in the audience may already know about the CCS 2009 study, which showed that an attacker can actually target a specific set of VMs, launch a bunch of VMs of their own, using the same interface that is available to other users, any other user, and achieve collocation with one of these target victims. But there are a few major limitations about the study. First obvious limitation is that it's 6 years old. There are a lot of things have changed since the last 6 years, particularly because of the study, which actually exposed many vulnerabilities and which were where the cloud providers have deployed new countermeasures like virtual private cloud, which provides better network isolation, etc. And apart from that, there is a general increase in the scale of these public clouds, both in terms of the size of the data center as well as the user base that is using these public clouds. And a minor limitation of this work that we also want to look at is that it looked at just one of the public clouds, which was probably only public cloud that was there then. And also, we want to address all these limitations in this work. And it's also important to note that there is also another paper that actually talks about a similar, is complementary and similar work that's going to be presented next, which proves the importance of this study. In this paper, we do a measurement study to understand if collocation attacks are possible in these modern security-hardened public clouds. And we take the perspective of an attacker and look at the steps that are required in achieving collocation. The first step here is finding the best launch strategy that increases your chance of collocation. This involves choosing the right launch parameters in the cloud interface. And the second is detecting collocation. Without detecting collocation, the exploit is not complete, because even if you achieve collocation, you're not able to detect collocation with the target victims, the attack is incomplete. It's also important to notice here that the placement policy is generally unknown, and it's a black box to any user. And the cloud provider also does not expose this information on collocation of two different VMs. So this makes this problem a lot challenging for a third-party user. So first, we will look at how we detect collocation in the study, as many of the prior attacks no longer work. And then we'll go ahead and look at the placement, the actual study results. So there are two important classes of co-residency detection mechanism. The first one involves reading the shared state between two VMs. This exploits a logical side channel where, for example, if there's a shared timestamp counter on the same host, you can read that and correlate between two VMs. Or look at the private IP address assignment. These were actually the attacks that were exploited in 2009 study. A second class of attacks exploits performance side channels, where two VMs, where you create a contention on a shared resource and observe a contention, the same contention on a neighboring VM to understand collocation. In this work, we take the second approach just because the first approach no longer works or is already fixed and easy to fix in public clouds. And we specifically use a memory-based covert channel, which was actually presented in USENIX 2012, which actually creates a huge degradation in performance. Let's first look at how this memory covert channel works and how we use to detect collocation. So let's assume that the attacker and victim are sharing the same host, and let's assume that the attacker runs a sender, which actually uses an atomic operation on an unaligned address. What happens when an attacker does this is that it, in many of the architectures, to provide atomicity, the architecture locks the memory bus. And when you run a set of memory accesses on a neighboring VM, you can actually observe this contention or memory locking that happens on a shared hardware. The performance degradation because of this actually can go as high as 3x to 4x, and this was used as a covert channel mechanism in an earlier work. But we use this for detecting co-residency. As you can see that the victim needs to cooperate to detect co-residency in this case, which may be fine for a measurement study, but for a realistic attack, it may not be that useful. So we want to make sure, apply the same technique for an uncooperative victim. That is exactly what we're going to talk about next. Let's assume that you want to detect collocation with one of the victims, which may be part of a huge cloud application, which is a set of web servers or key value stores, which is also multi-tier, where there is a back-end data store as well as a front-end load balancer. So any request from outside needs to go through the load balancer, which may be configured using a round-robin policy between these web servers. Now, the goal here in this realistic multi-tier cloud application, let's assume we somehow place the attacker on the same host as one of these victims. The task here is to use these public interface of this cloud application to detect collocation with the attacker. And to make this even harder, what happens if you do this when there is a background load on this application as well? So the idea here is that you use the same sender to create contention on the memory bus, but have an attacker run a client from outside and run a receiver, which is actually just a bunch of requests, and measure the latency of these requests from outside. So what we observe is that we can use the similar technique and apply it to a uncooperative victim, and this is the result of this study on EC2. We configured an application, a social networking application on EC2 with 3 web servers behind a load balancer. And here the x-axis shows the background load ranging from idle to 1,000 concurrent users on this cloud application, and the y-axis shows the average latency that is observed at the receiver, which is run by the attacker. And also note that the blue bar is when the attacker and victim are non-co-resident, and green is when attacker is co-resident with the victim. So what we observe here is that there is an extremely huge performance degradation as high as 45x, even in the presence of background load. This gives you a clear signal of that can be used to detect collocation in public clouds. And note that the y-axis is in log scale. So now that we have a tool to detect collocation with an uncooperative victim, let's go ahead with the actual study in finding if there is any a launch strategy which is beneficial for the attacker to increase his chance of collocation. The higher level idea here is that the placement policy is a black box, but we know that there are certain placement variables that might influence the placement policy, which ranges from number of VMs that you launch, or when you launch the VM, or which data center, or what type you use, etc., that influence collocation. And what we do here is that we fix these variables, do the actual study on a public cloud by using the tool that I just described to detect collocation, and repeat this for different placement variables. And we do this on the study over 3 months on the 3 clouds that I just described, and have spent more than $200 on each cloud. We use 2 distinct accounts. One is a proxy for a victim, which is used to simulate victim's actions, and other is a proxy for an attacker. And we explored 6 different placement variables, which is number of attackers and victim VMs, the delay between their launches, time of day, day of week, data center, and actually all the 3 cloud providers. And we do this for just small instances, equivalent small instances on all these public clouds, and the values of these values for these variables form a launch strategy. And we execute each launch strategy from a workstation at Wisconsin and detect collocation and detect and log collocation. It is important to note here is that we do 9 runs for each run configuration that spans 3 different time of day and 2 days of week, which is weekend and weekday. But before going into the actual results, I want to do a quick thought experiment with you guys. So let's assume, so what do you expect to happen in a public cloud? Let's assume for this thought experiment, let's assume that you have a random placement policy, which is probably the more secure that you can think of. And let's assume that you have a 50,000 node data center, which is actually the smallest number of smallest size data center in Amazon EC2. And there are you launch V victims and A attackers. The good thing about this is that you can actually calculate the probability of collision. And let's look at what happens when you vary the victims and look at how many attackers you need to launch to achieve a decent success rate of 50%. What happens here is that you almost need to launch 3,000 to 1,000 VMs to achieve a decent success rate of 50%. So let's keep this in the back of the mind when you look at the results. So now here I'm showing each run configuration on the x-axis where 10v20a means 10 victim VMs are launched and 20 attacker VMs are launched after 1 hour of delay on each of these clouds, and the success rate is on the y-axis. So what we see here is that even for 30 attacker VMs, we actually achieve 100% success rate in all our runs, which is the first really surprising result that we got. And it is important to note here is that it might look like Microsoft Azure is doing better, but this is actually a a side effect of our methodology, which I can explain later on. You can ask me a question on that. The overall takeaway here is that even with a modest number of VMs of 30 VMs, 30 attacker VMs, you can actually achieve a high, almost 100% success rate in achieving collocation. Let's look at what happens when we vary the delay between the victim and attacker launches. Where blue bar means 0 delay between victim and attacker launch, and green bar is for 1 hour delay between the launches. The first, for EC2, what we see here is that there is no collocation when you launch the attacker and victim at the same time. This is actually exactly opposite of what was seen in 2009 study, where they were able to achieve higher collocation when they launched at the same time. It might be the reason like they tried to explicitly fix that vulnerability. On GCE, it's also very similar, just that after a 1 hour delay, there is a higher chance of collocation, and there is non-zero collocation success rate for 0 delays. And on Azure, it's actually the reverse, where a 0 delay actually increases, has the highest collocation rate than 1 hour delay. And the important takeaway here is that each placement policy has a different, significantly varies, and you need different strategies for each placement policy. Now let's look at the cost of these strategies. The left graph shows the time taken to launch the set of VMs and then detect collocation. So on each cloud. So what we see here is that Azure takes a longer time. This was particularly because it took a longer time to launch, spin up a large number of instances at the same time. And on the right, we show the cost of doing the same, which includes time to launch as well as time to detect collocation. So important takeaway here is that we can achieve a higher chance of collocation even with as low as 14 cents, and on an average of 50 to 70 cents was sufficient to achieve collocation. Unfortunately, I was not able to go over other interesting results, which I would like to summarize here. Another interesting result was we were able to achieve collocation in all these launch strategies and in all the runs that we did on smaller data centers. This is also called regions in Amazon EC2's terminology. And another interesting result is that on EC2 we observed a time of day effect, where launching your VMs early in the morning actually has a higher chance of collocation. And on Azure, we were able to achieve collocation. We were able to place 16 VMs on the same host, which is probably all the VMs on that host. And apart from that, we also looked at platform as a service cloud as well. Heroku. A quick summary is that past clouds are also vulnerable to collocation attacks. And I would encourage to look at other strategies, interesting strategies that we found in our study. So far, we looked at how to measure and how to detect, how to find launch strategies, optimal launch strategies, and measure how much they cost us. But we haven't looked at how to compare different strategies and hence compare different placement policies or clouds. Here I'm summarizing a few of the interesting launch strategies that we found on EC2, where so the first strategy is launching VMs, 10 VMs, 10 victims and 10 attackers on a less popular data center, smaller data center. And the cost in cloud was 26 cents on EC2. And to compare against a reference policy, we actually measured the cost of achieving the same success rate on a random placement policy using a conservative pricing model. And what we found is that you needed to spend almost $100 more to achieve the same success rate in collocation for that strategy. And we can also compare the success rate of what is the success, compare the success rate between this normalized random policy and with the cloud. So to summarize, in this work, we revisited this problem of co-location in modern security-hardened public clouds and showed that it's still practical and, in fact, really cheap to do these co-location attacks, and in a way reincarnated all these existing work that actually is a prerequisite, which has a prerequisite of achieving co-location. And I would like to take questions if there's any.
Route. Jeremy Epstein, National Science Foundation. How many times did you run each of these tests? Is it the same day-to-day, week-to-week?
Overall or per launch strategy? So for each launch strategy, we actually run 9 runs. And each one's, so there are at least 3 runs that span different time of day. 3 runs per time of day. Right. Which is 3 runs for morning, 3 runs for noon, and 3 runs for evening, and also runs that fall in the weekdays and weekends. They equally fall, half of them fall on weekdays, and a little bit less than half on weekends. So. Okay,
and it's all in a relatively compressed time frame. I mean,
over 3 months, yes. Yeah.
So. I'm just wondering if some of the vendors were changing things around behind the scenes, how much would you be affected? How confident are you in your results?
So the suppressing, so I'm not really sure. Maybe I need to go back and look at it, but I think many of these results actually, even though I did run 9 runs, they actually spanned in a way across all the 3 months. Because I needed to rerun across all these 3 months. So it was a fairly long time window. I would be surprised if we caught a special case.
And when you did the 3 runs, they were fairly consistent.
Yes, yeah. And I was planning on showing a demo after launching those 30 VMs on Amazon EC2, but I think it's fairly reproducible.
Okay, good. Thank you.
Thank you.
Hi, I'm Simon Bodger from VMware, so we have an interest in this kind of stuff. Okay. You described for the non-cooperative victim, you measured the latency by making requests. Can you tell me a little more about the kind of requests you would make?
Can you repeat the last part?
The kind of requests that you would need to be able to make to the victim?
Sure, yeah, that's a really good question. So we didn't really need it to do special work to find the set of requests. Because in this case, what I did was I actually just went around clicking the actual social networking application and logging the access logs and just replaying that. The list of requests that I sent, the length of the requests were around 250 requests. Each one was consisted of image and everything. So it didn't require any special treatment. It just was a large number of requests such that you hit memory and observe the contention created by the sender. Yes, so it was fairly simple.
Well, since you brought it up earlier in the presentation, what was it about Azure that made your initial analysis problematic?
About the result?
Okay,
so what happened with Azure result was the 1 hour delay results are not exactly 1 hour. They are more than 3 hours delayed. That was partly because of the low success rate we saw on Azure. And the reason why that happened is that we actually reused the same victims that we launched for 0 delay and we ran the experiments for 0 delay, which took a lot longer than 1 hour on Azure. And hence, it's kind of a leapfrog experiment where we reuse the same victims and relaunched the attacker VM as though it launched after 1 hour for the same victims. So since it took longer to run the experiment co-residency detection for Azure, the delay, 1 hour delay wasn't really 1 hour, it was more than almost 3 hours. 3 hours for almost all runs. So that was the reason we see a huge drop in the success rate.
All right, if there are no other questions, let's thank Venkat.